Hello. In this video, I'm going to review homework 3. So, I know its due date is not coming before the midterm exam, but I think you need some guidance to prepare for the midterm exam. So I'm recording this. So I don't mind if you just use this video when you do the homework. So this is homework 3, and there are 3 questions, and chapter 3 was a very general estimation problem. So you can think it as a kind of example, just an exercise, solve the examples for the generalized framework, and it'll be pretty straightforward application of the theorem. So here, this is the answer that I typed yesterday. And you know what? When I make a homework, like not myself, but maybe most of the professors make questions without but do not write the answer usually. So when I write down the answer, then I find many errors in the question. So when I make the question, I don't know. Like say, I cannot. Like I did not expect a certain assumption is required, but later when I do answer it, I find actually something was needed. So it was a good experience to myself. And so first question is pretty simple: linear regression by minimizing the mean squared error. So so in chapter 1, we learned identification of the classical linear regression model. Now we are going to consider a different setup. We would like to show that beta 0 is the unique minimizer of this expected squared errors. So to see that, I'm going to use only 3 assumptions. So the result is pretty straightforward, but what I want you to see here is that I only use the assumptions. So many students are confused what is available, what is assumed, and what is a result of that, and what we need to show, right? So we say, for example, we assume A, then using A we would like to show B, then as a result of B we obtain C. So A implies B, then B implies C. But many students say something like, because of C, we have B. So the flow of the logic, flow of the rationale, the argument can be very confusing. But that's why you are learning this, like basic models. I'm using the same simple example to help you understand the logical flow. So try it, see it, how it works. So we have 3 assumptions, nothing new, just the same assumptions we used to have, and the criterion function defined this way. And then we are going to show that beta 0 appears only here. This beta 0 will be the unique minimizer of this function. And to show the unique minimizer, we need to check the convexity of the function, strictly convex, and then first order condition is satisfied. So derivatives, standard derivative, by the way, I remember Q is 1-dimensional, but beta is K by 1 dimension. So the dimension should match, and this is K by K dimension. So derivatives are straightforward. And first, let me check the second order condition first, which is pretty simple. We do not have beta anymore, and what we need to show is that this is strictly positive definite. This matrix should be strictly positive definite, and it follows from a lemma in linear algebra. So suppose that matrix M is a K by K symmetry and positive definite matrix. If it's non-singular, invariable, then it is strictly positive definite. So if you learn linear algebra, there are a lot of different some different statements of invariability, like strict positiveness. Many of them are linked to each other, also related to each other, but this is one of them. And you need symmetry to say this. So invariability and strict positive definite is equivalent for symmetry. Like to be more frank, to be more rigorous, if for a symmetric matrix, non-singular, if it is non-singular, then the matrix is either strictly positive definite or strictly negative definite. But in this case, like covariance matrix is always positive definite, so it is strictly positive definite, right? So second order condition is simple, and then first order condition can be written in this way, and I'd like to show that the first order condition is satisfied at beta 0. So this is the argument. You know, the derivative is another function of beta. Derivative function is another function. So the argument of the function is beta, right? This is the argument, and it is a generic beta, but here it is beta 0. At a specific, the true value, the derivative becomes this, and this equals to x epsilon using the linearity assumption, and this is exogeneity assumption. So this is it. Then like we completed the proof by showing that the second order condition is satisfied, and then the first order condition is also satisfied. So beta 0 is a unique minimizer of a strictly convex function. And as you can see, I used full rank assumption for the second order condition and the other two assumptions to check the first order condition. So this is how we approach to this problem, and you may now you see why we need to show this. Based on this, we can develop the least squares estimator. This is the theoretic identification. So this is the population level justification for least squares, because a true parameter minimizes the true criterion function. So we are going to obtain the estimator by minimizing a sample criterion function. So that's what we do. Okay, I will stop the video here. In the next video, I'm going to do question 2.